All right, chapter 3, molecules and compounds. So we learned about atoms last chapter, and we're going to learn about ways that we can put them together. We've got a quote from Francis Crick. Almost all aspects of life are engineered at the molecular level, and without understanding molecules, we can only have a very sketchy understanding of life itself. So understanding how the submicroscopic world works will give us a better idea of how the microscopic and macroscopic, the world that we live in, behaves and exists. So even if you're not going into chemistry as like your major and you're going to do a biology or just something kind of vaguely related, having some understanding of chemistry is still very helpful because it gives you an idea of some of the nuts and bolts of the microscopic world. So elements, which have their smallest unit as atoms, can combine with each other to form compounds. Combinations of any of the 91 elements that exist, generally, allow for an almost limitless number of compounds, since you can combine 1 and 1 of something, or 1 and 1 and 1 of something else, or 2 and 1, or 50 of just one thing. Any number of combinations and possibilities and permutations and rotations and things. There's lots and lots of ways that we can make different compounds. If we look at hydrogen, oxygen, and water, we can see that there is a large difference in the way that these compounds behave. So if we put 2 atoms of hydrogen together, 2 atoms of oxygen together, or if we combine hydrogen and oxygen to make water, they've got extremely different properties. So the properties of just hydrogen and oxygen, those have boiling points of negative 180 plus degrees Celsius. If we look at how those behave when we combine them, it's 100 degrees Celsius. Drastically jacked up the boiling point. Their states, of course, are also different. Hydrogen and oxygen are gases at room temperature. Water is a liquid at room temperature. Hydrogen and oxygen are both explosive and very flammable, and water famously is used to extinguish fires. So the way that the properties can change, even just by, like, if we added in another oxygen to our water molecule, suddenly it becomes hydrogen peroxide, and it's good for whitening teeth, but you probably shouldn't drink it. It would probably be very bad for you. So there's lots of interesting things that happen when we change around the composition of chemicals. So we've got 2 words. We've seen mixtures before. A mixture is elements just mixed together. They're simply next to each other, they're interacting with each other, but they are still their separate and distinct elements. It's kind of like colors of balls in a ball pit. You haven't combined the balls together, they're just kind of sitting next to each other, interacting with each other that way. And then we've got compounds, which are when we combine them, chemically combine them, to form something that's got fixed and definite proportions. Most things exist as compounds. Compounds are very, very common. And the fixed and definite proportions part is important. Like I said on the previous slide, right, water, H2O, it's got 2 hydrogens, it's got 1 oxygen. If you add 1 more oxygen in there, it's no longer water, it's a different compound. In this case, it would be hydrogen peroxide. So every compound is going to have a specific ratio, a specific proportion of the elements that make it up. These are held together by chemical bonds. There's 2 types of chemical bonds that we'll talk about. Chemical bonds result from attraction between electrons and protons. We'll learn more about bonds and how we theorize about them later in the class. The 2 types of bonds that we have that we're going to go into depth on are ionic and covalent bonds. These are 2 separate categories of bonds. The first one, ionic bonds, occur primarily between metals and nonmetals. Where do we find metals on the periodic table? Kind of more to the left side, the lower left side of the periodic table. Where do we find our nonmetals? Kind of in the upper right section of the periodic table. Also, hydrogen is often lumped in with nonmetals. So ionic bonds occur between metals on the left side, nonmetals on the right side of the periodic table. These involve the transfer of electrons. So an electron is transferred from one atom to the other. When metals interact with nonmetals, they typically transfer one of their electrons. So one of the properties we learned about for metals is that they tend to lose electrons or donate electrons when they go through chemical reactions. So the metal loses electrons. Those electrons have to go somewhere, and the where is that they go to the nonmetal. And so now we've got positively and negatively charged ions. The metal becomes a cation, a positively charged ion. The nonmetal atom becomes an anion, a negatively charged ion. And just like with magnets, positives and negatives stick together. So it's the positive and the negative charges that they have that causes them to stick together as ions. So they're stuck together like magnets. When we have the solid phase of an ionic compound, something that's made up of ionic bonds or connected by ionic bonds, they're connected in what we would call a lattice. So there's 3 dimensions, even at the tiny, tiny, tiny level. And so we get positive and negative charges kind of repeating in a 3-dimensional structure. The structure differs depending on how many positives, how many negatives we have. So an example is sodium metal. Sodium is a metal. It's a very soft metal. You can cut it with a knife. Chlorine gas is a toxic gas. If you combine these two together, neutral sodium normally has 11 electrons. Neutral chlorine normally has 17 electrons. The sodium, because it's the metal, is going to donate an electron to the chlorine. We know that it's going to donate 1 because of where it is on the periodic table. We'll get into that more later. And so it becomes the sodium plus ion. And then we get the chloride ion, Cl minus. And those stack positive, negative in 3 dimensions until you run out of positives and negatives. And that's what causes them to form the crystal structures that salt has. So that's ionic bonds. Covalent bonds are sharing. So covalent bonds involve the sharing. So that co part in front, like cooperative, coordinated, going together. So these are sharing bonds. We'll learn what valent means later. And these occur between 2 or more nonmetals. We are not going to be having any metals in our covalent bonds. Covalent bonds are only for nonmetals. Sorry, metals, get your own thing. Metals do have their own thing, it's just sitting next to each other. So when a nonmetal bonds with another nonmetal, there's not a transfer of electrons. They go in together and share electrons. The covalently bound atoms make up a molecule, and unlike our ionic compounds where it's a constant sea of repeating positive, negative charges, our molecules are distinct and separate. Molecules are independent units. They're separate from the other molecules. If they're in the solid phase, they might line up, they might stack up with each other, but it's not the same sort of attraction that we get between ionic compounds. Covalently bonded compounds we call molecular compounds. These bonds are not fixed either. So what we're seeing with these depictions here on the bottom is typically we're going to have our electrons. We've got our electron depicted by a little yellow dot. The electrons are typically going to be found between our two nuclei. The positively charged things here are the nucleuses of the whatever the atoms are. Our electrons are typically going to be found in between our two nuclei. You might sometimes find them outside of where you'd expect them to be, but most of the time they'll just be between. Kind of like two people shaking hands. Usually if you're shaking hands with somebody, you just stick your hands straight out and you shake hands. You're typically not going in for an above the head, upside down shaking hands, or like shaking hands kind of like sideways or behind your back. Okay, so each of these compounds can be represented with a chemical formula. Chemical formula indicates the elements as symbols present in the compound and the relative number of each as numbers that trail the symbol. So these will be in the form of subscripts, so they're slightly lowered and trailing the atom that they represent. For example, water is represented as H2O. The hydrogen gets written first by convention. There's a set of rules for like the order that you write things in. Usually you just learn it as you go. So the H with the 2 behind it means that we've got 2 hydrogens. There's not a number behind oxygen. So we just assume that it's 1 oxygen. Just like with dropping the E when we write mole for the short form, we typically tend to leave off ones and just assume that there's 1. It also makes it a little bit clearer because we don't always have subscripts. So it's easier to see when we just have one thing. Provides a little bit more texture to our chemical formulas. And we can see in sodium chloride, we've just got 1 sodium, we've got 1 chloride. In carbon tetrachloride, CCl4, we've got 1 carbon, we've got 4 chlorides. Or 4 chlorines, rather. In one of those molecules, one of those compounds. We do have a couple of types of chemical formulas. 3 types that we'll talk about. We've got empirical formulas. Empirical means experimental, basically. Not in the same sense of like experimental art or music, where they're like trying a new thing. More like it came from somebody doing a chemical experiment. This is what you'd come up with if you did the experiment in the lab to try to figure out what the formula is. And the empirical formula gives the relative number of atoms of each element in a compound. So it's got simplified subscripts. So for example, for hydrogen peroxide has the actual chemical formula of H2O2. But we could simplify that to get the empirical formula of HO. So we have to reduce the subscripts to get the empirical formula. And that's an empirical formula. Sometimes the empirical formula is the same as the actual chemical formula. The name of the actual chemical formula is the molecular formula. So the molecular formula is the actual count, the actual number of atoms, the real number of atoms of each element. And we've got some examples of molecular formulas and empirical formulas. So for example, C4H8, the greatest common factor of these subscripts is 4. We can divide both of them by 4. So divide both of them by 4, and you're left with CH2. So that would be the empirical formula. For B2H6, the greatest common factor is 2, so divide the 2 and the 6 by 2, and you get BH3. Sometimes it might take a couple of steps to reduce if you don't use the greatest common factor. For CCl4, carbon tetrachloride we saw earlier, the only common factor is 1. We only have 1 carbon. You can't have less than 1 of a thing in a molecular formula, and so the empirical formula is the same as the chemical formula, the molecular formula. So empirical formula and molecular formula can be the same. And then we also have several types of structural formula. You can sort of think of this as a picture formula or a visual formula of a chemical compound. So in a structural formula, at least one of the types, we'll be using lines to represent covalent bonds. So lines connect atoms where bonds would be. And we can have a single line, we can have double lines, we can have triple lines, you can even have 4 lines. I don't think we're going to see any examples of 4 lines. But you can have 1 bond, 2 bonds, 3 bonds. Rarely you can have 4 bonds, but again, I don't think we're going to see that in this class. Okay. So the type of formula that we use kind of depends on context. The structural formula actually has the most information in it. However, it's not always the best formula to use because you do have to try it out. So for example, for C4H8 that we were looking at before, drawing out all 4 of the carbons and all 8 of our hydrogens could be a little bit of a chore, but since there's multiple ways that we could arrange these, we could have carbon to carbon to carbon to carbon plus some double bonds. Don't copy this down, probably. So this is one way that we could arrange it. And this is different from a different version of arranging those. So this is why it communicates most information. We currently don't have the tools to understand how these two things are different necessarily. I mean, I do, but we haven't learned the tools yet. But these two are different compounds. And once you get familiar with looking at the structural formulas, it's almost as good as just getting the name. There's also some like ways that things behave that you can pull out once you've got the practice based on just how it looks. And C4H8 doesn't convey which of these two structures we're talking about or other possible structures we could have. An empirical formula is going to communicate the least because CH2 as an empirical formula could be C2H4, it could be C3H6, it could be C4H8. Any of those could be the molecular formula, and we wouldn't know which. So the empirical formula doesn't really give us that much. It just kind of gives us, at the base level, the most simple level, what's the ratio of the different elements to each other. All right, let's get some practice with empirical formulas. Write empirical formulas for each of these molecular formulas. All right, so we want empirical formulas for each of these molecular formulas. So we have the molecular formula. What is an empirical formula? Yeah, we would need to reduce as much as possible our subscripts. So we want reduced subscripts when possible. So C5H12. Do 5 and 12 have any numbers in common? Only one, the number 1. So our empirical formula is C5H12. How about Hg2Cl2? Yeah, these both have 2 in common. So HgCl is our empirical formula. How about C2H4O2? This also has 2 in common. So CH2O would be our empirical formula. Questions? All right, we'll stop there.